Hey there, I'm Arvind Chandra at Exun and I welcome you to the Exun Talks. Exun Talks are a series of interactive webinars and talks during the Exun week. These are conducted by professionals across a truly dizzying array of topics and of different types, from game development to future in automation. With constant interaction, it is a fantastic experience for everyone involved. To know the date and timings for the upcoming Exun Talks, please check out exun.co/talks. Here's a message from our sponsor before we start the talk.
Good evening, everyone. My name is Kanchi Khanna, and I'm the Senior Director of Admissions at Plaksha University. Plaksha is proud to partner with Exun 2021-22, and also it feels great to be among so many young tech enthusiasts. I'm sure you're waiting to hear from Aditya, who's coming up next, but I just wanted to leave you all with a little food for thought and a little bit about why I'm here today. So every year, about 1.3 million engineers graduate from various engineering colleges across the country. Studies show that about 70% of them are not even employable because of the way the subjects are taught, and also because industry requirements have dramatically changed from what was earlier being taught and now what needs to be taught. Many of these disciplines of engineering, whether they are electrical, mechanical, or civil, the way they are taught and applied was relevant decades ago. But today, when one looks at engineering applications around us, whether it's drones, robotics, engineering studies really need to be reinvented. The whole element of rote learning to experiential education should come into engineering, we feel. The founding of Plaksha, we hope, is a step in that direction. The world needs more technology, more engineering, not less. But clearly, there's a huge gap between what colleges are teaching and what the industry needs. So, a very high quality private effort in engineering was much needed. With those thoughts, Plaksha was born, and it's a collective endeavor. The university is founded by a trust with over 80 donors, and there are entrepreneurs from all over the world, like the Silicon Valley, New York, Singapore, Hong Kong, and other places. It's a large group, and we're expanding. We've come up on a 50-acre campus in Mohali, and it's envisaged to be both a teaching and a research institution. We've crafted new disciplines of engineering, and we aim Plaksha to become the fountainhead for entrepreneurship, new ventures, startups, and innovation. Research at Plaksha will be focused around big problems, whether it's the problem of healthcare or agriculture or manufacturing 4.0. So, really, the big problems that India and the world face. Can technology help solve them? Can you, young students, help solve them? The four majors that we offer, they are computer science and artificial intelligence, robotics and cyber physical systems, biological systems engineering, data science, business, and economics. If you look at these majors, and if you think of all the engineering disciplines, you'll see that those disciplines are hidden in these four majors in a very amorphous way. Like, take robotics and cyber physical systems, for example. It incorporates mechanical, electrical, electronics, and computer science, and the same is true for the biological systems engineering. Even in the computer science and AI, the emphasis is on AI tools that every engineer needs to learn today. It's the foundational engineering course for all four majors. Or take the data science, economics, and business. Everyone knows that engineering drives economies. It makes sense to make data science, economics, and business come together as one major under engineering and technology, because that's what's really driving things. So it's this kind of interdisciplinary training that the industry is demanding, and every business is talking about digital transformations. But graduates are either siloed in economics or they're siloed in technology. We really need to bring them together. You don't have people who can do both. Bio, we've seen COVID pandemic has told us how it's come to the center stage. The confluence of data and biology is what's driving the vaccines, which used to take 9 years and now developed under 9 months. So there are a lot of other elements that go into making these programs holistic. We are also integrating designs, system thinking, liberal arts, so that the kind of learning that you get at Plaksha is very, very holistic. Of course, math is going to be central to all programs. We hope that Plaksha over time will become the torchbearer of what technology education can be. The name Plaksha itself reflects the idea of the university as a tree from which a river flows endlessly. And I'm going to stop here. Ashwin, if you could just put up a short video that we have of Plaksha. I hope that we do see applications from many of you coming into Plaksha. Thank you so much.
Thank you, ma'am. I hope you all found it interesting. Now, today with us, we have Aditya Sengupta. Aditya, an alumnus of UC Berkeley, currently studying in Cambridge, was the president of EROS, the Airspace Society of Deepest Archipelago, and a member of Exun clan. Without further ado, here's Aditya.
All right. Hi, everyone. Really excited to talk to you all today. And I'm also excited to come back to Exun, which is where I learned about programming and a lot of the ideas that I'm going to be talking about today. Now, when I was in Exun, I wasn't really in the programming division. I wasn't that involved with it. I was there as a quizzer. But then I got into college and I initially thought, well, I'm going to be doing physics and astronomy. That's what I was interested in. And I didn't think I really need to go too deep into programming. But then it became clear to me how much of a useful tool it was and how it was really underpinning everything I wanted to do. So I'm going to start off by giving you a few examples of, things that I found cool in the ways programming has been used in science and has really pushed forward a lot of new discoveries, especially in the last 10, 20 years. So first off, the one I know the least about, but that I find among the coolest, is that you can use IBM's quantum computers online right now. I decided to put this up front just in case there are people who are like, oh, I'm not really interested in this and wanted just one takeaway. If you want just one takeaway from this whole thing, it's you can go use a quantum computer right now if you Google the Qiskit library. This is something I had to use for a class, and I found it really cool. You need some basic level of Python to be able to understand it, but it's really well documented, and you can run experiments, and you can observe all these effects like quantum entanglement that seem very abstract unless you put them into practice. And it's really enabled a lot of research in this field. But okay, that's kind of like, this is computer science research. What about physics, which is what I said I was talking about. Here's my second example. This is one that I actually came across in my research. Astronomy data sets, in this case, the Kepler data set, where they're looking for transiting exoplanets, are mostly open access. Anyone can go download them and see exactly what we found. So this is a quick sample from the Kepler data set of, these are the planets we found. Are they confirmed planets? Are they candidates? Are they false positives? And there's a lot of other information about them. And people have taken that and used that open access data and done a bunch of complicated statistics on it, but it's all ultimately, in this case, it's Python programming. And they figured out answers to some really cool questions, questions that I'm really invested in as research goals for my career. Like, what is the frequency of planets like Earth? So this over here is P for period, which is how long is a year on that planet. So over here, it's approaching, there's fewer and fewer detected planets the longer the period. And it actually stops before we get to planets like Earth. But these kinds of studies are what we'll need to find, Earth 2.0 that's out there. And this one, similarly, it's radius of the planet in Earth radii. And this one, we're biased towards seeing a lot more planets that are bigger, which makes sense. So it's really cool that you can use computer science and you can see these results, and anyone can do that. And a third example, one that got me really excited about the use of computer science in astronomy, especially, is this project called Celeste.jl, which I came across in my senior year of college, where basically they took all the data from this mission called the Sloan Digital Sky Survey, SDSS, which included pictures of the entire sky, everything we can see. And it has 188 billion stars and galaxies in it. And what they needed to do was they needed to build a catalog from it at each position. Is this thing a star? Is it a galaxy? If it's a galaxy, is it spiral or elliptical? What's the color of the star or galaxy? And so they built up this graphical model and they ran it through one of the Berkeley supercomputers and they processed it in 15 minutes, the entire sky. And they made this massive catalog of everything we can see, basically. So, especially in the last 10 to 20 years, astronomy has really been pushed forward, physics as well, has really been pushed forward by computer science. And when you start doing research, you'll be given a bit of starter code and you'll be told, do this simple thing and then do the slightly more complicated thing, and you build up and build up. And it's basically a big software project that you're doing. So I hope I've established that research programming is important. But now, sorry, I'm going to adjust. I'm told my aspect ratio is a bit off. Okay, how's that? Is that better? Oh, you're not seeing presenter view. Sorry, just giving a moment, technical difficulties here. But I'll keep talking while I try and do this. So hopefully I have established that research programming is an important thing to understand if you're trying to, wait, I'll just go back to the entire screen, it's fine. Okay, research programming is really important if you're trying to do research in physics and astronomy. But what does that actually entail? In this talk, I'm going to give you 4 big ideas of what it entails, of how you can make your research programming better. The first one is going to be vectorizing your problems. The second will be just-in-time compilation. The third will be improving the algorithms you use. And the fourth will be interpreting it for the purpose of science and reproducing it. These are ideas that I've picked up from physics and astronomy research, but they're useful no matter what kind of programming you're doing. So one more thing. This is clearly very much about code and about coding, but I'm going to do my best to make it accessible regardless of your level of experience. And this is not only a good thing so that you can get something out of it no matter where you are, but it's also very much to do with one of the core principles that you learn when you start doing computer science, which is the language you're using isn't as important as the ideas that you're trying to encode using that language. So with that, I'm going to first define a term that I'll use quite a bit, which is a function. A quick working definition of a function is it's a bit of code that takes in some input and returns some output. It's a black box bit of computation. I put in something, I get something else out. So in this case, I've got a function named square that squares numbers. You put in a 3, you get out a 9. And you're not really supposed to care what happens inside or how it's doing it. Like in this case, there's not going to be that much diversity in how you do it. Like maybe you have x times x, you have x squared, or in Python, you'd have x double star 2, maybe. But it doesn't really matter how it's done once you've done it. Once you've written the function, it's a black box, and you should only deal with the function and not really care about what's inside it. So that's what's called an abstraction barrier. So those are just a couple of terms you might use. And I wanted to get our working definitions out of the way first. So here's our first big idea, vectorization. One type of operation that you're going to do quite a bit is applying one function to a lot of different data points. And in your first CS class, you'll be told to do it with a loop, a for loop or a while loop or something like that. You have a list of things, say, in this case, the number is 1 to 3 or 1 to a million. And you're going through and you're applying the same function to all of them. I take 1 and I pass it through this squaring black box, and I get out 1. I take 2 and I pass it through the square, and it's 4. 3 squared is 9, and so on like that. You can do that as many times as you want. But there's an opportunity here for a performance improvement, because I just care that in the end, I get these results of 1 squared to a million squared. I don't care what order I do that computation in, as long as I get out the right result. I don't need to do it in sequence. So, and it turns out computers are really good at not having to do things in sequence. So this is a general paradigm called single instruction multiple data, SIMD. And that's the term you can Google if you're interested in learning more. I'm not really going to go into the details of how computers do things, because I'm aiming to have more of a working guide of how you're supposed to use these things in practice than all the details under the hood. And I wouldn't be able to do all the details under the hood full justice in the time I've got anyway. But the idea here is computers can exploit the idea that they know where in memory this 1 is, where this 2 is, where this 3 is, to do it faster than if it was just, I have this array, take this 1 out, run it through the square machine, put it into another array, and do the same thing with the 2, do the same thing with the 3, up to 1 million. When you have just one instruction applied to multiple pieces of data, it's much, much easier. And the computer can do it much faster. So here's a more involved example with the dot product of two vectors. If I've got 1, 2, 3, and 4, 5, 6, the way to do it in for loops would be like this, like it's shown here. You do 1 times 4, and you save that result. You save that 4 somewhere. You do 2 times 5, and you save that result somewhere. You do 3 times 6. You save that result, and you add them all up. And that's a certain number of steps. But if you can do it in this single instruction multiple data way, you can first define the instruction, multiply this number by this number. You multiply the number index 1 by the number at index 1 here. And that's much faster now, because I'm taking these two sets of data and I'm applying the same instruction to 3 sets of data that I'm just doing it once. 1 times 4, 2 times 5, 3 times 6, all at once. And then I just have to save those results and add them up. And there's a more involved example here that it'd be a little bit intensive to go through step by step, but it's the same idea. It saves you a lot of computation when you're doing this, especially with multiple dimensions. So hopefully I've proven the point that if you do one instruction over multiple pieces of data, that speeds it up. And doing this and getting used to doing this requires that you sort of change your way of thinking about problems a bit in some cases. So I'll go to an example in a bit. Before then, I'm going to talk very quickly about GPUs. So a GPU is a graphics processing unit. It's a thing that they initially built for image processing, but then it turned out to process the images. And for example, for graphics in a video game, you need to be able to handle a lot of computations very fast. You need to be able to do quick square roots and squares of things, to use Pythagoras' theorem to compute distances between points. You need to figure out shading. You need to figure out how to render polygons. So there's a lot of parallel computations and a lot of things that have to happen very fast. So they built these custom machines to handle all that load. And it turned out that this was actually a very good machine for doing science. It turned out that a lot of these operations were exactly what we wanted to do for really big science cases and really big simulations. Now, is that just like a convenient thing that we found out? Did we just build these things and say accidentally one day, we accidentally came across this thing and realized, oh, that's exactly like graphics? Not really. The conceptual connection goes a little deeper. I'm not expecting that everyone's seen linear algebra before, but you've probably seen at some point systems of equations that look like this, where you've got a bunch of unknown terms, x1, x2, x3 in this case, and a bunch of coefficients, and they're related in this way. And what you can do is you can put those into a matrix and make that just a single equation on the single unknown with just this vector that includes x1, x2, x3 all at once. Now, a lot of problems in mathematics and physics and astronomy, and in all kinds of science and engineering, can be reduced to linear algebra. Fitting data is linear algebra. Taking a Fourier transform, analyzing probabilistic systems, analyzing when something vibrates and when it doesn't, that can all be linear algebra. And so there's a lot of work that's been put into making sure that computers can do linear algebra really, really fast. So there is our other takeaway for how we adjust our mode of thinking to fit the computer best, which is you want to reduce your problem to linear algebra as much as you can. You want to think about what's the problem you're trying to solve? Can I put it into a form that looks like this? Can I put that into a form that the computer likes? And if you can do that successfully, that'll give you orders of magnitude speed ups in how a computer does things versus just telling it to do it the naive way, which is what maybe your first instinct is. So here is an example that ties all of this together. This is the Monte Carlo estimate for pi. And it's called Monte Carlo because it's using probability, after the famous casino. Now, estimating pi, there's many ways to do it, but this is one of the most intuitive, I would say, which is you have this unit square. It goes from 0 to 1 in this direction, 0 to 1 in this direction. The area of this quarter circle that's sort of carved out by the red points here is pi over 4. You can just, it's pi r squared divided by 4, r is 1. So if you drop a bunch of points in there randomly and uniformly, and then just count up the number that are inside that quarter circle, that ratio should get really close to pi over 4. And you see, in fact, that it does in this animation. Not necessarily very fast, but it does it. And it does it probably a lot easier than some more fancy methods. So this is the one case where I'll have pseudocode, but it's no big deal if you just don't want to read that. But the important takeaway here is there's a loop. You have something to do n times, and you see here that that n is rather large. So this might not be the fastest way to estimate this thing. It'll do it, but not very fast. If you vectorize it, though, it gets a lot faster. And the reason you can vectorize it is no step depends on the previous one. I don't care when I'm putting this point down, or any point in here, where this point was. I can just pick all of these points up front and then figure out, are they in the quarter circle or not, and then sum up that ratio. And so now I don't need the loop in there anymore. I can just do it as a single operation on these big arrays of here's all the x points, here's all the y points. And this turns out in practice to be, I think, 20 times faster. It depends on your implementation, of course. But the key idea here is it's a lot of single instructions that operate on all of these data points at once. So that's very good for speed. Okay, so that's idea number 1, vectorize problems and reduce them to linear algebra as much as you can. Now for idea 2. This one is maybe one you might not have heard of as much. It's called just-in-time compilation. To understand that, we need to understand the 2 main modes that programming languages run in. One is compiled, which is I take a bunch of code that I've written and I translate it to machine code. That's called compiling. And then I run that machine code. Machine code is the lowest level representation of the zeros and ones that the computer actually understands, but that would be completely incomprehensible to a human. The other is interpreted, which is you read code and you understand it as you go through it. There's no real separate steps. Well, there are, but it's sort of hidden from you. It looks like it's just doing it all in one go. And there's sort of a trade-off here. Compiled languages are generally a lot faster. You've probably seen people talk about like C, C++, Fortran as being languages that are very fast, but they're not the most intuitive to code in. You have a lot of these ideas of you have to deal directly with memory and pointers to things and all that. And it's a bit unintuitive, especially if you're a scientist and you can't be expected to have a software engineer's level of understanding. You already have to learn everything you need to know for your physics. You can't really be expected to be an expert in 2 things, which is why interpreted languages are a lot more popular. There are things like Python or Mathematica, and those are used a lot more, but they suffer from this lack of speed. There's another problem with interpreted languages as well, which is they can't look ahead. If you have a Python script that's 500 lines long, which is not at all unusual, and you have some really small problem that you could have fixed, like a typo or something that got declared wrong, on line 500, you need to run through the first 499 lines first. And that can take a lot of time. And it can be really frustrating. I speak from experience here. It can be really frustrating when you see the sort of obvious error and you've just wasted hours and hours of computation and you can't save any of it. And you wish you'd have spotted that error sooner. Now, compilers fix that because they first compile and then they run. So any of these obvious errors can be caught at compile time. Now, there are tools, there's things like linters that will help with detecting these errors in Python, but that's sort of a half measure. It doesn't really work in every case. It doesn't completely solve this problem. So now the scales of the trade-off are a bit weighed in the compiler's favor. You want to use compiled language because it's a lot faster and you've got a stronger guarantee that you won't have errors. But On the other hand, it's so much easier to use an interpreted language. And again, we really don't want to put all our time into making physicists and astronomers learn these compiled languages and learn how to do it at the level of software engineers. No, they've got their science to focus on. So what's the solution here? The solution is just-in-time compilation, which is sort of a fusion of the two. When you run a just-in-time compiled program, it looks like it's using interpreted mode, but it's really compiling everything to machine code like a compiler would. As soon as it's run as an interpreter would run something, it saves an interpretation that the computer can use directly. And if you if you run that a second time, it won't look at the code you wrote again, it'll look at the machine code underlying that. And that's much faster. Now, a few of you who know me know that I'm really invested in the Julia programming language. I really like using it. I've worked with Julia computing, actually. And this is one of the reasons why. Just-in-time compilation is one of the foundations that the Julia programming language is built on. And it's why it's a really good language for scientific computing. And I'll talk more about that in a second. But if you don't want to switch, it also integrates decently easily with Python for some use cases. I wouldn't say most. I've run into issues with trying to just-in-time compile my Python programs. So I wouldn't say most, but there are definitely a lot of cases where you can speed it up without much overhead. Now, nothing's perfect. You don't get any free lunches. So the trade-off here is you have an execution cost. That first time you run a new bit of code, it's not just doing what an interpreter would do, it's also doing what a compiler would do on top of that. So you get a little bit of a slowdown the first time you run something, and then it speeds up the second time you run it. Now, that's not really a problem for scientists, because when we talk about speed, there's a couple different ways of interpreting that. One of the interpretations is just how long does your program take? But in terms of science time, I would say what really matters is how long does it take from you sitting down to do something to having it done? Which means you not only need to make the program itself fast, you also need to make the development time fast. You need to be able to prototype on something very quickly. And just-in-time compiling is very good for that. By contrast, if you're just using a compiled language, you might get a very fast program in the end. But if it took you 10 hours of learning something new to get there, well, you spent 10 hours on that when maybe you didn't need to. So this offers a solution that seems to be perfect for the science workflow of I'm going to write something and then I'm going to keep hacking it. I'm going to make one small change at a time. I'm going to add one bit at a time. I don't have to keep compiling the whole thing over and over again. So how do you use it in practice? Now, the code for integrating it into Python is surprisingly simple. It's using the number library, and that supports just decorating any function you've already written with this thing at ngit. So all you have to do is add these two lines to whatever you were writing already, and it will be just-in-time compiled if that's something it can do. And number is a very well-supported library. There's a lot of great examples on there, including, I think, the pi vectorization that I just showed you in the previous point. So you can go and try this out if you've got anything that's big and complicated and takes a long time. Go try it for yourself, see the speed up. The other way you can use it, in my experience at least, is Julia. Julia, as I just said, is a language that was written mainly for scientific computing. There's a lot of cool features. This isn't a promotional talk for Julia. I have done those. So I'd be happy to talk to anyone who's interested in it more after this. But for now, the point that it would be best to take away is it's a language that's fully just-in-time compiled. It's written from the ground up with the intent of being able to just-in-time compile everything, which makes it very good for this sort of science workflow. And the other Julia feature that's really interesting is multiple dispatch, which is basically operators doing different things based on their data types. And that is useful because it means we can cleanly define abstraction barriers. Remember when I was talking about functions, I said, once I've written a function, I don't want to know what's inside it. If I have to write something 5 different ways to work on 5 different types, I don't want to see that in my high-level code. I want as little of an idea as possible when I am working on a higher level function, what's happening at the lower level. I don't want to care, for example, when I'm adding two integers, about the specific bits that are being manipulated to get there, because the more access I have to that, the more error prone your processes are. The better separated things are, the more efficient programmer you'll be, and multiple dispatch is a really good way to do that. And just fun, here is the standard Julia benchmarks, which you can use to see this sort of trade-off in speed between compiled and interpreted languages. So over here, you've got C as our ultimate benchmark, as pretty much the fastest thing. You've got Rust and Fortran and Go as compiled languages that do pretty well. They do around what C does, and so does Julia by being just-in-time compiled and just very tightly written. And way over here, we've got our interpreted languages. Python, this uses NumPy over here, which a lot of it is written in C++, I believe. So that's why matrix multiplication is almost as fast here as it is in the compiled languages, because it's ultimately compiled. But generally, at most tasks, interpreted languages don't really pass the speed threshold that you might need. Whereas Julia, by being just-in-time compiled, gets almost all the way there, and in some cases better than the fully compiled languages. So that should give you some idea of the power of just-in-time compilation. Okay, now for big idea 3. We've covered what steps we can do to get to a mathematical result that we're interested in. Can we optimize what those steps actually are? Which is to say, previously I had an algorithm that I wanted to implement, and I could tell the computer to do that in a way that was better suited to its particular tasks. So can I change the actual steps that are happening to get better performance that way? There's a lot of cool examples here. Unfortunately, they would need really deep dives into writing down equations and drawing complicated trees, and there's a lot of theory behind all of this. So I'll skip over that, but again, if you're interested, I'm more than happy to talk about it later. But there's 3 main ways to do this that I've seen. One is do some smart mathematical tricks to gain an algorithmic speed up, which is what they did with the fast Fourier transform, if you've heard of that. Another is you can gain algorithmic speed up by cutting accuracy slightly. There's, again, a trade-off over here where if I'm okay with a result that's maybe 95% accurate that happens in 1,000th of the time, I probably want to do that. Or see if someone else has done it for you. And that last one turns out to be the answer surprisingly often. So I'm going to go slightly in depth into one case study over here, because it's by far the prettiest thing that I've got in these slides, which is n-body integration. N-body integration is a really cool idea that's applicable across a lot of different science, because it's the same basic laws, like Newton's law of gravitation or the equivalent law for electromagnetism, regardless of what length scale you're working at. You could be working with really tiny charged particles, or you could be working with stars and galaxies, and it's kind of the same thing. So if you solve an n-body problem, if you write something that can give you the trajectories of things that move under this inverse square law, that can be useful to a lot of science. Now, if n is 2, that's relatively simple to do. You do it in high school level physics of determining the orbit of the Earth around the sun, for example. You take their masses, you take their distance between them, and you work out g m1 m2 over r squared. With 3 bodies, it gets a lot more interesting, as you see here. This is one of my favorite things on Twitter. It takes initial configurations of masses and positions, and it does this computation to figure out where they're going to go if they're all gravitationally interacting. There's 3 gravitational interactions here. There is a blue, an orange, and a yellow body, or I guess that's more red. So at every time step, what it's computing there is the interaction between the blue and the red, the blue and the yellow, and the red and the yellow. So that's 3 bits of computation you have to do for every time step, which is not too bad. But then you scale up to 1,000 or 1,000,000, and oh, wait, I already want everyone to see this. I just really like the spot. Anyway, you scale up to an n of 1,000 or 1,000,000, and it becomes a lot more complicated, because now that number of interactions goes way, way up. It goes up with the square of n, because I've got the interaction of body 1 with body 2, 1 with 3, 1 with 4, up to 1 with 1,000, then body 2 with 1, 2 with 3, 2 with 4, 2 with up to 1,000, and so on. I've got a million interactions. If I had a million bodies, I would have a trillion interactions. And that quickly becomes way too much for computers to handle. This is kind of tough to speed up algorithmically because there's no really nice symmetry in the problem. Well, there is, but if you're going to use this approach of direct integration with Newton's laws, there isn't really. But maybe something you noticed in here is how fast that red one shot away. Yeah, there it is. Shot away from the blue and yellow. And the blue and yellow are sort of doing their thing. They're going back and forth and approaching and going far away. And they're not really caring what the red one is doing for a while, at least until the red one comes back in. So maybe based on that, you start formulating a hypothesis of, well, if I could get rid of the red term over here, I won't have to care as much and I can do fewer computations and get the same result. And that's borne out by the physics because in it, it's an inverse square law. If something's very far away, it probably won't have much of an impact. Now, there's a problem with this because in that case, the red body was, I think, the least massive of those. But if you had something way more massive out there, that would actually impact your results way more than you would like. It's a bit too simplistic to say, I am just going to ignore the thing, the third body out there, or in general, any body that's sufficiently far. It can't just be based on distance, it also has to be based on mass. So a more refined idea here is if you have a bunch of bodies that are really far away from the thing that you're trying to compute the interaction with, you group them together and you only look at their center of mass. In this case, I'm trying to compute the effect on M1 of these three, M2, M3, M4. And that's three terms, the ones in red, but they're all pretty far away. So what I'll do is I will combine them into their center of mass. I'll do a weighted average of their positions and their masses, and just say this is a point object with a mass M2 plus M3 plus M4 at the central point, and I will just compute this one interaction in purple. And if you scale it up, you get the Barnes-Hutt n-body computation method. The way you represent that in a computer is something called a quad tree or an octree for higher dimensions. And how it works is basically this. I've got this node here, and I see that that distance is much greater than this length scale of the size of the cell. So instead of looking at all of these points individually, or all of these points on the tree, I'm just going to look at their root node, which will have the sum of all of those masses in there, and it'll be at the center. So I'm just going to sort of prune all of this. I will not look at it. And that actually gives you an improvement from n squared interactions to n times log n, with some caveats on it has a term of d over l in there, but for fairly reasonable choices, it gives you that kind of speed up for not much of a loss of accuracy. So that's a really cool example of how we can think about our problems really deeply, figure out what's important, figure out what's not important. It's what you do when you're doing physics by hand, and it is equally what you do when you're doing physics on the computer. But really, most of the time, well, maybe not most of the time, that really depends on what you're doing. But a lot of the time, if you find yourself doing something tedious in any kind of programming, really, you often don't need to because of this idea of abstracting your thinking. When you're doing, for example, this n-body calculation, you don't specialize it to gravity or electromagnetism or any other kind of system that works under this inverse square law. You just think of it as the general set of things that work under inverse square laws, and you go look to see if anyone has done similar things. Or maybe it's not even an inverse square law, it's just anything where you have n things that are all interacting by some rule that you know. So the more abstract you get in your thinking, the more you can separate out which parts of the problem are and aren't important, the more you can get useful resources out there to help you with your problem. So for example, these are both things that I've seen done. People have written really sort of convoluted things to try and approach something that other people have already solved much faster because it's a very generic problem that they've written a really fast solution for before. So always make sure you're going to look for those first. And that leads me nicely into my fourth big idea, which is using code as a science tool. I'm talking a lot about programming here because it is probably most of what you do on a day-to-day basis as a physicist or an astronomer. But we have to remember that code isn't actually the result that you're producing. Code is a science tool, and like any tool, it's got its particular flaws. It can have errors, it can have biases, you can use it wrong. There's a lot of different things that can go wrong when you're coding, as anyone who's done any coding will attest. Which means it's just as important to write good code in the first place as it is to verify and validate what you're doing. I don't know if verification and validation is exactly the term in computer science, but it's what the term is in engineering and simulation. We want to know if the code met the task we were trying to get it to do, and we want to know if that task served the science goal. And another really important aspect of this is our code results need to be reproducible. When I run something and I get a result, I want to be sure that if I run it again, that I will get the same thing. Because if it was just, something that you can only get once, that's not really something you can rely on. And it's often not the case, this is thankfully changing, but in the past it has often not been the case that we have this guarantee. And it's really important for the foundation of science that we have it. As experiments go more and more towards being computation, we need to know that they are actually up to the standards of experiments in the sense of things you would do in a lab before. So how do these things work? Basically, it comes from asking yourself questions and setting up ways to answer those questions for your particular program. So I like separating out asking myself questions about the science that I'm doing and asking myself questions about the code. So with the science, maybe for that n-body interaction example, I would give it an n equals 2 case of like the Earth and the sun masses and the radius of its orbit. And I would see, does it recover the actual behavior we see of the Earth going around the sun? Can I reproduce simple results that the program gives me with just pen and paper calculations? Or I might try implementing something in 2 different ways and seeing if I get the same results. In that case, it might be, I do that very long computation of all the n-squared interactions, and I compare it to the Barnes-Hutt approach, and I see, are they within 1% of each other? Because for a very simple case, they should be. Equally, I should ask myself questions about the code. I've talked now a few times about separating out different ideas and abstracting your thinking a bit. So you need to make sure throughout that you're actually doing that. You need to make sure you're testing each step individually. You need to make sure that the steps are well separated out. There's no sort of hidden dependencies that are really easy to creep in. And you want to make sure that your functions are actually, black boxes that you put in the same thing, you get the same thing out. I also just like how passive aggressive these emails were to me this one time. Travis CI, CI for continuous integration, is a tool that will automatically run tests for you and will make sure that if you've got a program that's building on your machine, that it will build on other people's machines as well. And sometimes it doesn't. Sometimes they send you emails like that. It's kind of fun. Okay. Now, when we're talking about reproducibility, I need to talk about Jupyter Notebooks.
Right. So our speaker's battery just died for a second. We're getting him back as soon as possible. Thank you for your patience. He'll be answering questions soon. So be sure to stay.
Hey, can someone from the Exun team tell me if I'm back?
Yeah, you're back. Right.
Cool. Okay, follow up. Can anyone tell me where I was when I dropped off? Sorry about that.
Yeah, I'm just checking.
Or can anyone just drop in the comments what was like the title of the last slide they saw?
Testing and verification slash validation.
Okay. Oh, right after. Okay.
No, right after that, reproducibility and Jupyter notebooks. You're starting that slide.
Okay, right. I'll start from there then and just pick that up, and hopefully you can just edit this back together later. Sorry for the inconvenience, everyone. Right. Wait, I'll just wait a minute to confirm that people can see this now.
Yeah, we can see clearly. Yeah.
Awesome. Okay, right. Picking back up then, sorry for the inconvenience there. Right, I was talking about Jupyter Notebooks. Now, Jupyter Notebooks are very possibly how you learned how to do programming initially. It was definitely how I started to do programming once I left school. In school, I learned on the RTP students will probably remember the days of having to learn Turbo C++, and hopefully things have progressed since I was there 5 years ago. But one of the main ways that I learned how to do programming, especially for science, was using a Jupyter Notebook. Now, Jupyter Notebooks are great tools. They're basically, you have a bunch of cells and you can run them individually, and they build up to some end result, whatever you want to use them for. And you can run one cell and then run a second cell that depends on it, and the third cell, and you keep looking at the intermediate output and keep trying new things. And so it's great for hacking on. But it's really, really easy to misuse Jupyter Notebooks, like I've done in this example here. You can probably see what I did if you used them before, which is basically I have, a equals 4, a squared equals 9. That's going to look right. So what I did here, you can see by the execution order, I first set a is 3, or maybe it was -3, you don't even know that. Then I ran a squared, and then I went back and changed the value of a. So this is what you could call an inconsistent state of the program. And so this leads to serious problems when you're actually doing a much more intensive science case. When you're hacking and you're going back and forth and changing things, it can be really easy to forget the actual execution order you used. So you don't know if things are based on, you don't know if your results are based on hidden variables that only exist because of your specific execution history. And that can make reproducibility really difficult. This is not to malign Jupyter Notebooks as a tool. They're really useful. When I'm teaching computer science-based things, I love lecturing off them because it makes it really easy. If someone asks me, what would happen if we changed this? I can just do it live for them, and we see exactly what happens. So they're really useful for lecturing. They're really useful for demonstrations. They're really useful for hacking, but they should be used with some caution for the final science result that you're trying to go for, or any kind of result you're trying to go for. One possible way to alleviate this is going back to Julia as an example, is the Pluto notebook, which is a project in the Julia language that basically aims to solve the persistent state problem. So you see here, they're updating this variable automatically. This n to the power -2 that depended on it updates along with it. So if you change a cell, if you change your first cell, then the second cell that was depending on it updates to match that. They're also pure .jl files, so you can run them as source files, which I find really convenient. So this is a project I like a lot as a way of getting around that. So to start wrapping up, I'd like to talk a bit about my personal computational science project lifecycle. I don't always strictly adhere to this, but it's sort of aspirational and some things you could try to do as well, which is you start prototyping in a Jupyter notebook, you maybe write a few functions or do a bit of data processing. And Once you're satisfied with the results you're seeing in that notebook, you start moving them over to source files, .py files, .jl files, whatever else you're using. And the advantage of that is once they're in there is no more dependence on execution order. They're just individual bits of computation that you can call on whenever you like. And this is really going back to, once again, it keeps going up, abstraction barriers. The less I have to think about what's happening in the source file, the better. I don't want to keep rerunning all these function definitions every time I open my Jupyter notebook up. And instead, I just want to think about, this is a thing that I can do, that I have defined how to do, and I'm not thinking about how it's happening. It reduces the mental load of having to program new things as well. After that, you make a Git repository and a GitHub and commit to it often. This is something that I could do a whole other hour on. Many people have. There's lots of good guides on Git and GitHub out there. And so I highly encourage doing that as well. And the other advantage of moving everything to source files is you can write tests. And the more tests you write, the more of these previous verification and validation guarantees you'll be able to tick off. And once you run into a bug, which you invariably will, or if you try to write something new and you go back to this prototyping stage, you can build on your already work in the source file in a new notebook. And so this is a little bit of IPython code that I add at the top of every notebook that actually surprisingly few people know about in what I've come across. It's called IPython Line Magic, which I think is just a delightful name. And what this basically does is it makes it so that if you change something in my science package, which is the thing you're importing, then that change gets immediately reflected without any reloading in the Jupyter notebook you're using. So this is a really useful little tool for if you're prototyping anything in Python and a Jupyter notebook. So to start wrapping things up again, let's summarize what we've learned. Now, I haven't been at all exhaustive. I haven't covered every aspect of being a good scientific programmer you could be. I haven't covered every aspect of the things that I have chosen to talk about today. It's impossible to do that much in an hour. But here's some takeaways that you can hopefully start applying to your own projects. One is take advantage of what your computer knows how to do really well, which we saw in the vectorization case, and we saw with reducing everything to linear algebra as far as you can. Another is building on what others have done before. Be opportunistic and look out for things that people have done. Think about the most general version of an idea and see what's out there already. Is there software that's particularly suited to your goals? Are there algorithms that other people have written that you can adapt? Anything you can do to reduce the amount of customized work you need to do is probably going to be better, because that means you can save your effort for the really novel parts of your project that really need it. Make sure you have a good understanding of your tools. Use the right one at the right opportunity. If you see there's a process that's being run 1,000 times in an interpreted language, you might try to vectorize that. You might try to use just-in-time compilation, or depending on what it is, you might try a more advanced algorithm that doesn't depend on the execution order. So keep in mind what the capabilities of these things are and try and think about when they might be useful. Also, keep in mind that you're trying to do science, and so every bit of programming you do is going to influence the science. Make sure that you're making assumptions that are well suited to your science goal, for example. And finally, probably like the least novel and interesting one, but the most important one, is make everything easy to use and maintain. Your future self will thank you for that. Any collaborators you're working with will thank you for that. It's just a good thing to do. So with that, I'm done. A couple of final points here are the material on Julia is my own. I wrote it before I worked for Julia Computing, and so it doesn't reflect any of their opinions. Not that I think it could, it's just informational, but just in case. This talk was based on a student-run class that I taught with my friend Ali Kuda at UC Berkeley last spring. So there's the course website. If you want to check out 13 hours of me and him talking about all this stuff in much more depth, you can go there. And thanks a lot to him. Thanks a lot to all of our students. And finally, get in touch. If anything seems interesting, you want me to expand on anything here, or you're like, I want to do this specific thing, or I want to get into scientific computing generally, contact me. There's my email. There's my Twitter. I'm open to talking to anyone. So thanks very much. All right. Seems like we have questions. With just-in-time, is memory an issue with the need to constantly maintain and edit a parallel machine code? It can be, but if you're worrying about memory at that scale, it's not an exponential increase as far as I know. Like if you have memory problems, then you have memory problems with the initial implementation anyway, and you need to upgrade your hardware in some way. So it might increase it a bit. It doesn't increase it by orders of magnitude. Does multiple dispatch in Julia imply the ability to have a more flexible input in a single function capable of dealing with slightly different cases? Yeah, that's exactly what that's exactly what it tries to do. Yes, the idea is if you're really interested, they have a whole system of types, and what multiple dispatch really means in practice is if I'm writing a function, I'm going to say add. I can write add of a an int and b an int. I can write add of a string and b a string. Those will do different things, but will have the same syntax. So that means I can sort of encapsulate a bunch of different desired behaviors under a type tree. And I can just refer to all of those things at once with the generic function name add. In Python, if you wanted to do this, you'd probably do like add underscore int, add underscore string, things like that. And they've made some exceptions for like the plus and the star operators, but broadly, they don't have that separation because Python's dynamically typed. Do you think that today's youth lacks innovation and that today, because of that, the world lacks unique inventions? I'm not very qualified to speak on that, but I wouldn't say the world lacks unique inventions, really. I think, if you've got something you're interested in doing, you can absolutely do that. I'm not very qualified to talk about society in general. Sorry. Okay. Is there a method to determine how much computation time is based on the parameters, like relative distance after which you combine? Yeah, that would get pretty heavily into like specifics of if I want to like analyze a particular algorithm, like the n-body algorithm, then you can put sort of asymptotic limits on that. But that's more of a case-by-case thing and would need a whole lot of development of the theory of asymptotic analysis. So those methods are out there. That is much more a formal computer science thing. I'm here just to give you sort of a usable toolkit for if you're not a computer scientist so much. Okay. And does Julia work as a suitable replacement for languages like MATLAB and Simulink in engineering applications? It's trying to get there. A lot of things, this is getting into actually things that I don't think I can talk about. But yes, that is one of the aims, is to replace things like MATLAB for engineering applications. That's like, my subjective opinion is the one thing that MATLAB has over anything else right now is Simulink. And anything else, you're better off using Julia or like some sort of Nova accelerated Python in some cases. But Simulink is like way above anything else for its specific niche. But Julia is definitely trying to catch up there. It's a relatively young project. It's about 10 years old, and MATLAB has decades on it. But it'll get there in a few years maybe. All right, I think that's all the questions.
Yeah, that was the last question. Thank you, Aditya, for such an amazing talk. I found it very insightful, and I hope our audience did too. Thanks for joining in, and I hope all of you enjoyed this session. More amazing stuff coming up this week. See you at the next Exun talk.
Thank you, everyone.